I'm a PhD student in astrophysics at ASU. I graduated last May with three bachelor's degrees in astrophysics, chemistry, and French. I work over at the Arizona Science Center on Blue Crew, so I basically get paid to do cool things like light my hand on fire and blow things up, which is a pretty cool job. I also have had two jobs at NASA. The first one was at the Lunar Reconnaissance Orbiter as a graphic designer, and then I'm currently working for a mission to Psyche, and I manage our archiving, events, and all of our exhibits and outreach. So, to go into the research, we're looking for life in the universe, but the universe is really big, as I'm sure you're familiar. And when we're looking for life, we're not only looking for microbial life, but we're also looking for multicellular life like plants, and even complex, intelligent, multicellular life like humans. But there's one place in the whole universe that we know for sure has life, and that's our planet Earth. And if we know Earth has life, shouldn't we look for other planetary systems like our own so we can look for another Earth? So, how can we find other potentially habitable planets like Earth in the universe? There's four kinds of exoplanets that we've discovered. So it's going to be gas giants, super Earths, Neptune-like, and terrestrial. And Earth falls into this terrestrial category. So you'll notice we've only discovered a very small number of Earth-like planets in the first place, 4%. So 96% of what we discover is significantly larger than Earth. And just a quick note, we've found over 6,000 planets as of September of last year, which is super awesome. So, how do we discover these exoplanets? There's a couple of different ways, but today we're going to focus on the transit method, which is our primary method of detecting exoplanets. As you can see here, it's this green bar. It's our most successful way to discover them. So, really, star, and we're looking for a decrease in the amount of light that we observe. So we're not directly seeing this exoplanet, we're seeing the effect that it has on our observation. And what's really cool about this method is it allows us to calculate the size of the planet and how fast it orbits its star based on how big the dip is. So we can get a lot of cool information from this, and we've discovered a lot of planets using this method. And one of the ones that is really famous is the TRAPPIST-1 system. And what's really cool about this system is it has multiple Earth or super Earth-like planets that are within the habitable zone. So the area where liquid water exists, where we're expecting to look for life. But there's a really big problem with the transit method. And it's that all of the planets we find are very, very close to their stars. So the entire TRAPPIST-1 system fits within the orbit of Mercury, which is our closest planet. So these are extremely small systems. To give you another scale, the closest planet in the TRAPPIST-1 system is about as close to its star as Callisto is to Jupiter, so in the Jupiter moon system. So these are very, very small. And our solar system is not so small. So if we were to observe our solar system using the transit method, this is kind of what we would see. So we would be able to detect Jupiter, even though it's pretty far away, it's pretty big, so it would block out enough light for us to detect it. Neptune, we could see it. It would be hard, but it's there, and Earth just blends right in with our observation of the star. Um, so basically, what we're seeing here is it's nearly impossible to discover Earth using our leading exoplanet detection method. And I just want to point out the y-axis of this graph right here. Look at how little light is really being blocked out. So it's just a very, very small percentage or fraction of a percentage. So our telescopes are really, really awesome to be able to detect anything this small, but they're not sensitive enough to detect Earth right now, which is what we're looking for. So how can we detect Earth-like planets if we can't actually see Earth using this method? So there's a couple of main issues with the transit method that I just want to go over really quick. So first is time. So ideally, we would want to observe the exoplanet transit 3 times or more to confirm it. Now that would mean pointing our telescope to discover Earth, pointing our telescope for 3 years in the same place. And if you're familiar with the time that people get on telescopes, it's going to be more in the span of hours to days if you're lucky. Definitely not anything as long as this. So it makes it very difficult to find long period planets or even just like Earth-like ones that are a bit longer than a couple of days. The next problem we have is perspective. We can only see them if they're aligned so that they block out any light at all. If we're looking top down and the planet never crosses in front of the star, from our perspective, we'll never discover it using the transit method. We can use other methods, but again, the transit method is our leading method, and it just means that we can't see everything. Then there's also the size preference. So the transit method is easier to discover large planets close to a small star because it blocks out more light. But that isn't what our solar system looks like either. We have small planets close to a pretty big star. So a quote from an observatory is only about 10% of hot Jupiters are aligned so that we could see it. So we're already only seeing a very, very small fraction of planets that are out there. Smaller planets are even less likely to be aligned. So the fraction of things that we can discover, we've discovered a lot, 6,000 plus exoplanets, but it's still such a small amount of what's actually out there. So this has bothered me for a while. So I'm like, what can we do to account for the bias that is created with the transit method when we're discovering exoplanets? So to do that, we're going to need a little bit of context about how planets form. So planets form in what's called a protoplanetary disk. So this is a disk that surrounds our baby star, our protostar, and it's made of mostly gas and dust. And over time, this material will accrete into planetesimals or a baby planet, and then into a planet itself, and the disk will dissipate. And what's really important about this disk is made of the same material that the sun has available. So the disk and the star are made of the same things. So we'll touch back on that in a second, so just keep it in mind. So, in our solar system, we can kind of break it down into different kinds of materials. So, our terrestrial planets, like Earth, are rocky planets made of silicates and iron, these really heavier materials. And then we have Jupiter and Saturn, which are the gaseous planets. They're made of hydrogen and helium. And then we have our ice giants, which is water, ammonium, and methane. So, what I'm proposing is this will allow us to predict what the protoplanetary disk of our solar system would look like. Because, of course, we can't go back in time to actually see that. But we can map out where those elements might have been in our disk. So we could say the terrestrial planets formed in the inner disk using silicates and iron that were on the inside. The gaseous giants played are formed in the middle with hydrogen and helium, and then the icy giants formed on the outside with water, ammonium, and methane. So if we can backtrack using simulations and modeling to figure out where these elements were in our protoplanetary disk, we can look for other protoplanetary disks with the same composition. And that way it doesn't rely on observing these difficult to find planets. Instead, we can just look at the composition of the disk, which we can already do. So, how can we create these planetary system simulations? So first of all, we can look at a star and determine what it's made of. We can look at it and figure out the chemical composition. And from this, like I said earlier, we can figure out what that disk is made of because they form from the same material. So you can use a software like Moog to get abundances if you're curious about names of programs. And so once we have our disk, we can figure out what the planets can make. So we know what materials are available. So that material is what forms the planets. So then we can figure out what kinds of planets there can be, what kind of geological activity could be on these planets, because that's very important in maintaining life. Having a core that can move and heat the planet, or even like tectonics, things that can kickstart life almost. So once we have our models, we can figure out the planetary interiors using software like Exoplex, and also comparing it to known abundances of chemicals on exoplanets that we've already discovered. So we've taken composition of a star and taken that to probability of habitable exoplanets. So this is a really powerful way to look for these exoplanets by just using a little bit of math and a little bit of code. So this project is actually working towards the Habitable Worlds Observatory, which is like a James Webb scale mission that will launch in the 2040s, hopefully. So what my part on that project is looking at our list of target stars, about 100 stars, and I'm going to figure out which star has the highest probability of having these habitable Earth-like exoplanets so we can dedicate more time to looking at those stars to find those specific planets. So, to go back a little bit, when we said we can compare to protoplanetary disks, we see tons of these. So these are what real protoplanetary disks look like using the ALMA telescope. So what I'm hoping to do is if we can make a ratio, so if we say um, a fifth of the protoplanetary disks that we see resemble what our solar system's protoplanetary disk might have looked like, and one-fifth of them are not like our solar system, then we find 100 planetary systems using the transit method or another method that are not like our solar system, that formed from these protoplanetary disks that were not like our solar system. We can extrapolate and approximate that there are 400 solar systems like our own that we haven't been able to discover using our detection methods. So, just a little bit of statistics, a little bit of math, we can figure out that even if we can't see these directly, we know that they're there. And these are those systems that probably could have an Earth-like planet. So, if our hypothesis is rejected or if it's not, we'll still learn a lot. So if this protoplanetary disk thing doesn't work out, it won't all be for nothing. So we'll learn a lot about other types of planetary systems and how they form, how common it is to have an arrangement of planets like our solar system, so terrestrial on the outside, gaseous, or terrestrial on the inside, gaseous on the outside. And we can learn more about how planets form in the first place. So, what does this mean for our search for life? So, we can look at how many other habitable planets are there in the first place? What's the probability of forming these Earth-like exoplanets that could have life on them? So, these are like our huge questions that we're asking right now. And hopefully, this project can shine a little bit more light on those answers. So, in summary, what we're going to do is we're going to simulate forming planets from composition of a star and different protoplanetary disk compositions. And from there, we can find the probability of having a planetary system like our own, like our solar system. And then we can find the probability of finding a habitable Earth-like exoplanet. Do you guys have any questions on this before I move on to a slightly different topic?
Yeah, I do actually have one. Could you go back to the slide that had with the protoplanetary disks, the separation of all the
Hmm.
different materials there?
Oh,
Uh,
this one right here?
yes.
Yeah.
With all of that, I see like the silicate iron, and then it goes out to more gaseous. And
Hmm.
I'm assuming that was the icy was kind of gaseous. Does the mass or the type of material depend on how far out it goes in the planetary disk? Is it like I don't want to say heavier, but more massive material stays in?
So that's a really good question. That's actually something that I'm hoping to incorporate into my project. So it actually kind of leads into the next thing I'm going to talk about. but I've worked with a mass spectrometer before, and for the mass spectrometer that I worked with, that I'll talk about in a second, our lighter things move farther and faster, and our heavier things move slower, and they just take longer to reach it. And that's how we can separate the masses of the things that we're studying. And I think that a protoplanetary disk should behave the same, especially as you have material migrating inwards. The heavier material should go farther, but I hope to look more into that.
Okay, thank you.
Yeah, of course. Any other questions? You can put them in the chat or unmute. It's up to you guys.
I
Okay,
think we'll get to move on.
awesome. Oops. Sorry, guys. I don't know where my slide went. There we go. Okay. So I've done something similar to this in the past, but in a bit of a different context. So now I'm going to tell you a little bit about the research I did as an undergrad, also here at ASU in the School of Molecular Sciences. So it's a similar question. My big question is, how did life begin? So once we find our habitable exoplanets, we got to figure out, how does life get there? Does life get there in the first place? What conditions do we need to form life in the first place? So that's my big question. Our little question is, can peptide bonds form between amino acids using only radiation from the sun? So that's a pretty intense sentence. So we're going to break it down just a little bit. So first, what is an amino acid? An amino acid is a building block of life. So when you have a bunch of amino acids chained together, you start forming proteins, which is the basis for forming DNA. So this is something that is really important when we're looking for life in the universe because we need these amino acids. What is a peptide bond? A peptide bond is that bond between two amino acids. It's just a fancy word for the bond. Um, and then radiation from the sun. Our sun puts out infrared, visible, and UV. These are the ones that we're just going to focus on specifically for the portion of this project. So, why is this relevant at all? So we found organic molecules, including amino acids, on asteroids in our solar system. So these are not habitable places as far as we know. They've got no atmosphere, no life on them. But we have found almost every single amino acid required to build life as we know it. So we have amino acids, the building blocks on asteroids, and we have complex life here on Earth, but we don't know how to get from one to the other. So that is where this project comes in. So for example, for this project, there's a lot of amino acids. We're focusing on, for this all intents and purposes, the simplest amino acid, which is called glycine. So here is neutral glycine, and neutral molecules are really awesome to find, but they don't really do the things that we're looking for. A neutral molecule isn't going to form the bonds that are required to make life. So we're looking for charge separated glycine. And how do we get from neutral to charge separated? To do that, you have to add some number of molecules of water, but we don't actually know how many molecules you need. There's a huge debate in the community about this because everyone's getting different numbers. So, what I did was I tried to figure out this exact number of water molecules. So, how did I do this? I used this giant laser that we built. So, here's me standing in front of the laser. Of course, we have a laser cat because I love including that in here. So, to break down our laser a little bit more, the first thing is we have our YAG laser. So this is going to basically blow up our sample. So our sample's going into this vacuum tube, and the YAG laser hits it and blows it up into a bunch of little pieces that we can then use for the second part. So we have our TI Sapphire laser. So this does something that's really cool. In a delay box. So we put it through a second harmonic generation crystal. So basically, we're just splitting it into 400 and 800 nanometers. And the 800 nanometers is the red line on the bottom. And this goes through a delay stage. So we can change how in phase or out of phase our laser beams are with each other. And this allows us to probe different states of the atom. And I'll talk about that in a second because this laser stuff is very confusing. Um, so then our laser beam goes into where all of our stuff was blown up earlier, and it excites these molecules. So our molecules then get shot up through another vacuum tube, and they go into our mass spectrometer. And this is where we start having them separate based on the size of the fragment. And this is really important. So that data looks kind of like this. So it will tell us the exact weight of each fragment that hits the mass spectrometer. So remember how we needed to find the number of water molecules. We know the mass of water. It's 18 AMU. It's H2O. And our mass spectrometer tells us the masses that it interacts with. So we can figure out exactly how many water molecules are going to be there to form these peptide bonds. So this is the perfect setup to study this question. So our other part of our data is looking at the recovery time after the molecule gets hit by the laser. So I'll break that down for a second. So normally our atoms are in what's called the grounded state. That's this left figure. And then when they get hit by the laser, they move into the excited state. So our electron moves up in energy. And this is what we're looking for. So this orange line is pointing to what we call time zero. This is when the laser hits our sample. So that's that big peak in the upper right corner. And then we have a relaxation period. So over time, our electrons will relax back down to the ground state. So we can measure that in the slope that you see in that top right corner of the data picture. And then we take measurements every couple of, it's usually like a femtosecond. And so those are all the little tiny dots that you see in the actual data, again, in the right corner. Are there any questions on this? I know the laser is like very overcomplicated.
Yeah, would the laser basically be like how we use a spectrograph, except you're using it with matter instead of light?
I think so. Yeah, I think so.
Okay. Yeah, because
Yeah,
everything
that
else
makes sense.
seemed the same, but it was just we don't, yeah, we just take the light.
Yeah, so we're using not the light, we're using actual atoms. Okay, so one thing I do want to point out is if we go back and look at the wavelengths of our laser, there's something really important that you might notice. And that is our lasers, 400 nanometers, 800 nanometers, 532 nanometers, are going to be visible, infrared, and UV. So these are the exact same types of radiation that's put off by our sun. So our laser has the same radiation as the sun, and our vacuum chambers are doing our best to emulate space-like conditions. So everything happening in here could happen out in space. So we're not making a huge stretch with material. So we'll just keep that in mind. So what we're expecting, because I started this project right before I graduated, so it's very much not done yet, is a two-step process. So a one-step process looks like our ethanol on the left. This data is from an old project I did, so this isn't working with our amino acids. These are just examples. So a one-step process is you just have a bond breakage. A two-step process is going to be something like a rearrangement and then a breakage. So that's what you'd see with 1-butanol, for example. So this is step one. It's the fast step. So that's going to be a rearrangement. And then step two is the bond breakage, and that's a slower step. It also will form a new bond usually. So we're expecting with our amino acids to see a two-step process like one pensional, where we see that rearrangement where it goes from like this to more like a ring. And then it also has a second step that's a bit slower that breaks off a molecule. So, for our amino acids, what does that look like? So, this can be a little bit confusing to look at because it's just a bunch of letters. But each of our pink boxes is an amino acid. So, we have amino acid 1 on the left, amino acid 2 on the right. So, it's important to have different things on different sides because it's not a symmetrical molecule. So, that's what those circles are from. But we don't need to worry about that right now. So our first step is the bond breakage. So that oxygen molecule will break. And then our second step is a rearrangement. So we form water at the bottom, and then our amino acids form the peptide bond and connect with each other. So in the end, we get two amino acids bonded together by one peptide bond. And once you have a bunch of these, then you formed your protein. And then once you have a bunch of proteins, you can then form your DNA. So what does this mean? We can figure out how many water molecules are needed to allow these amino acids to bond together using our mass spectrometer. We can also see if peptide bonds can be made in space-like conditions from only radiation from the sun. So this doesn't require any other catalyst other than our water molecules in the sun. So it can happen just in space. Um, so I think that is all that I have for you guys. Do you have any questions?
Did you guys happen to try this with anything other than water?
As like adding into it?
Yeah.
I don't think we had. So most of my time starting up this project was adjusting our laser to be able to actually complete the things that we needed. So we hadn't tested a lot of different kinds of molecules or different options or iterations of what we were putting in there by the time that I graduated.
That makes sense. It'd be really cool to see with different types of um like liquid.
Yeah, I think that's a great question. It would definitely be something worth exploring.
Actually, now just expanding on that, what would be something that you can do like deuterium or something like that? Because I'm trying to think what would actually make those bonds.
That's a good question. I think, hmm, yeah, I mean, maybe because there's already like the OH in there, like the stuff for water is in there. Um, but yeah, I'm not sure. We tried with different carrier gases. Um, so we tried like I think helium, and I think we tried xenon and a couple others too. But that doesn't really have too much of a difference on what's going on.
All right. Anybody else have any other questions?
If you need, if you change your mind about questions, my email's at the bottom of these slides. So feel free to shoot me an email with any questions. I'm happy to respond to just about anything. So just let me know.
Can I ask you a question about the program that you mentioned, Moog?
Yeah,
Uh, is that this might be a dumb question. Is that like a Python package?
I wish it was. It's in Fortran.
Okay.
So what I do is I run it through terminal. So I have historically had many issues getting Moog to work on my computer. I think they have started making Python wrappers for it though, because of course Fortran's a bit outdated. But for what we're doing, Fortran is much faster.
Oh, interesting. All right, thanks.
Yeah, no problem.
All right. Yeah, Ellie, that was awesome. Thank you
Thank
so much.
you.
And I will be posting this on our YouTube also in the next day or two. Yeah,
Awesome.
yeah, because I really like this. I think a lot of people will be interested in this.
Cool. I'm so glad that you guys liked it. I know the laser stuff can be really hard to understand, but if you
Yeah,
have
but
any
who doesn't like
questions,
lasers?
I know it's so fun.
Yeah.
If you have any questions, please just email me. I'm always available.